let's begin. So first of all, thank you everybody who is attending today, the CAMWorks 101 webinar. This is going to be about an hour long introduction to CAMWorks. So it's nice to see some familiar faces, people who I've worked with in the past, and it's nice to see some new names here as well. This is going to be a great intro to CAMWorks if you are unsure of exactly how it works or what it is, or if you have a bit of experience with the software. This is going to be a very realistic look at programming parts. This isn't really meant to be a demo, but instead actually working with the software and using it for real. But there is going to be a little bit of an introduction at the beginning here. So the agenda for today is introduction. What is CAMWorks? Who is GoEngineer? Who am I? And a little bit about how CAMWorks operates, its features, its benefits. And then we'll go into the live demo portion of the webinar, and this is going to be the bulk of the webinar. We're going to be programming a mill turn part. So if you're unfamiliar with the CAMWorks terminology, mill turn would essentially be a part that's cut on a lathe with live tooling. So we're going to go through and we're going to program. I think it's a pretty neat part, and it's going to be very realistic. It'd be exactly how I'd program this part. And so I want you guys to really get an idea of, if you haven't seen the software, how you can use it. And if you have been using the software, maybe you can pick up some tips and tricks, or maybe throw some questions my way. Again, because this is a webinar, all of the attendees will be muted, but you can ask questions in the chat window in the GoToMeeting dashboard. This is also going to be recorded so that you can view it later when we upload it to our YouTube page. And then the last part here of the show is we're going to show, this will be the very first time CAMWorks G-code machine simulator has been shown to the public. So I have a copy on my machine. I've had a license for just a couple days now. I'm still learning how to use it myself, but this was just perfect timing to show a sneak peek as to what it can do, and give you an idea of what to expect from it. This is going to be something that is completely new for CAMWorks and really all CAM packages out there at this level. It's a true G-code machine simulator. So we'll show that at the end. So who's GoEngineer? You might have somewhat of an idea who we are. We are a company that specializes in manufacturing tools, namely SolidWorks, Stratasys 3D printers, Altium, Electrical Designer, CAMWorks, and Agile PLM. We have over 25 years of experience doing this, and we have customers in hundreds of industries. One of the great things that we have at GoEngineer is what we call our jumpstart program. It's essentially a program to help new customers get on their feet using the software. We normally come in and do training on site, or you can come into our offices and we do training, we do implementations, and we get you running with the software as quickly as we can. We do that in our offices all throughout the western United States. We have, since this graphic was created, we actually added 2 offices, one in California and one in Phoenix. So CAMWorks, that's what we're here to talk about, right? So CAMWorks, we're going to go through just a few of the highlights of what it is as a software. So CAMWorks is a CAD neutral machining package. Okay, what that means here is that we can work on SolidWorks files, obviously, but we can also use CAMWorks on STEP or IGES files, Pro-E files, Autodesk files, Solid Edge files, CATIA, Creo, NX, anything that you can bring into SolidWorks. That's the important thing here. CAMWorks is fully integrated into SolidWorks, so this is a great tool for current or prospective SolidWorks users. We'll see here in the software that switching between SolidWorks and CAMWorks is really just changing a couple tabs. Alright, so the big thing that CAMWorks has going for it is its automatic feature recognition. CAMWorks was the first CAM company to develop auto feature recognition. back in the first version of, I think it was 1997, right around the time SolidWorks started. The CAMWorks feature recognition is more advanced than what you'll find anywhere else. So there's a lot of feature-based CAM softwares out there now, but they won't find the same features that CAMWorks does as consistently as they do. If you go to SolidWorks and you ask them the same question, they'll probably give you the same answer, considering that they actually license the CAMWorks feature recognition for their own add-in called FeatureWorks. If you've ever brought in, say, a step file or a Pro-E or Autodesk file or a Solid Edge file, it comes in as an imported body, and SolidWorks will ask if you want to build a feature tree. Well, that's CAMWorks feature recognition running in the background there. The next step to this feature recognition is the fact that we use a database in the background to keep track of your best practices. So we call this the TechDB, or knowledge-based machining. Essentially what this is as you program your parts, you can teach CAMWorks how you program, and it will pull those best practices in for you automatically in the future. So if you're programming family of parts or family of features, it can really decrease the amount of overhead and the programming time immensely. I'll show you some examples here during the live demo so you can kind of see how that works. The big idea here is that we teach CAMWorks how to machine like us, and it automates it in the future. We have some high-performance toolpath options, so namely VolumeMill. A lot of people are familiar with VolumeMill. It's a big name out there. These are going to be high-performance toolpath that are all tangent-based, and they are essentially there to allow you to cut faster. So it's going to reduce the cut time. It's going to increase your tool life. This is a great tool for people who are chugging out a lot of material, cutting deep pockets, or starting with billet and just carving it away. VolumeMill is a great tool for them. Finally, we can add this last item here, the true G-code machine simulators. So every CAM package out there does a built-in simulation, right? We live and die by it. We program the parts, we simulate it, we watch the tools remove the stock, and then we can even run a comparison against the original file, and it will show us how accurate we are. But then at that point, we always translate what we see inside SolidWorks, or what we see in whatever CAM we're using, into a language that our machine tool can use. We call that G-code. And that translation is a step that can introduce some inaccuracies, right? So really what we need to simulate the G-code. Eliminate that translation and eliminate that source of inconsistency or error. And that's what we can do here now, is that we can actually post the G-code and we can simulate it in a machine simulator. So again, it's not only simulating the part, but it's simulating the entire machine environment, so that we can check for interferences between, say, our tailstock and the turret, or the gang tool holder on our lathe against the stock or the chuck. It will check all of that. So it's truly an amazing product here. We like to say we're the complete CAM solution. So that kind of leads me into this next slide here, and I got just a couple more. CAMWorks can basically do it all. When it comes to milling, we can go from 2.5 axis flat bottom features to full simultaneous 5-axis features. Within that milling package, we offer VolumeMill, as I mentioned, and we also offer a nesting program. So if you're a woodworker, or if you like to cut out multiple parts from a sheet of stock, we offer nesting programs. We also do turning or lathe work. We can do 2 or 4-axis turning. So 2-axis would be your standard lathe, and 4-axis would be a dual turret lathe, front and back turret. And then in that 4-axis, we can sync those front and rear turrets. So if you need to make a cut on the ID and the OD of a part simultaneously, for example, we can sync those turrets together using the sync manager. Combining the turning and the milling, we have mill turn. As I mentioned before, mill turn is basically creating parts on a lathe with milling tools as well as turning tools. And that's what we're going to show you today. And I elected to show a mill turn part because it shows you all of it. It shows you turning, it shows you milling. It shows that when it comes to mill turn, it's not only front and rear turret, but also sub-spindles as well, so we can do transfer parts. And then we have the wire EDM module. We can do 2-axis and 4-axis wire EDM. Kind of encompassed in all of that, we have a product called the Universal Post Generator that's included free with any version of CAMWorks. This is a way to allow you to tinker with your own post processor if you choose to do that, or edit your own post processor. And then lastly, all of these are covered under the G-code machine simulator. Actually minus the wire EDM, but turning and mill turn and milling all fall under that G-code machine simulator. So real quick, the benefits here, and I'll kind of let the demo speak for itself. The benefits here using CAMWorks is, one, we're going to be reducing the programming timing. We're going to be machining a part that is fairly complex. It's an aluminum bicycle wheel hub. Fairly complex. We're going to be doing it within the span of this webinar, and I'm kind of going to slow it down as well to talk about what I'm doing here. So if you're already a CAM user, what I'd like you to do, and if you're looking at CAMWorks as a possibility, try to think in your mind how long it would take you to program this part using your system. Reducing scrap. This comes along with having that technology in the technology database in the background, keeping track of our best practices, so that when we go to program parts, we use tried and true strategies. Increase quality, same sort of instance there, same reason. Reducing the tooling cost. This comes into, again, standardizing what we're doing. If we have a team of programmers with the TechDB that's shared, we can ensure that the quality and the work and the tooling that everybody uses is consistent. And reducing lead time. That goes along with the programming time here. So with that, we'll go into the live demo. I just like to show this this last slide here. CAMWorks is compatible with all the major machine tool dealers out there. So if you have some obscure Italian woodworking machine, we can work with that. If you have a Haas, welcome aboard, because that's probably the most common machine we work with. Mazak, Makino, Doosan, we do it all. So we have posts that are compatible with your machines. So with that, we're going to jump into SolidWorks. And before I begin, just a reminder that chat window's there. I'm going to do my best to keep an eye on it. If you have any questions, feel free to speak up, and I'll address them when I see them. So for the SolidWorks users out there, this should look fairly familiar, right? This is the SolidWorks window. We've got the SolidWorks feature tree along the left-hand side here. We've got the part that's been created inside SolidWorks. But as I mentioned, it's not a requirement that the part was created inside SolidWorks. So if you're a job shop, or if you program parts that come from other sources, don't worry. We can do imported bodies, no problem. Moving over to CAMWorks is essentially just moving tabs. So we've got the CAMWorks tab up here in the ribbon style toolbar, and we have the CAMWorks feature tree here. I'm going to zoom out. We can see that we get a representation of the chuck. I have this set up right now for a mill turn machine. A mill turn machine. That's a 2-axis mill turn machine, so no y-axis. By choosing that machine, it also chose my tool crib, so the tools that I've told CAMWorks I have on that machine. It's chosen the post processor as well. I also got my stock here. So I kind of set this up beforehand, but this is normally something that you would have to do when you first open a part. This is going to be a turn part with some milling features on them. So we're going to be cutting this from bar stock. It's cord. Right. So again, this is an aluminum bicycle wheel hub. So to give you an idea of the stock, it's about 3 inches diameter and 4.5 inches long. And this is 60-61 aluminum. Right. If I zoom out here, you can see we've got our sub-spindle chuck over here 20 inches down. So at some point, I'm going to program in a transfer where the sub-spindle comes and grabs the part, pulls it back to its home, and then we machine the opposite side. And we're going to be able to do this all in one program. So for right now, I'm going to turn off the chuck display. And we'll begin working on this part. So I mentioned the auto feature recognition. This is a great tool that to start out with, right? I usually open up CAMWorks, check to see that I'm in the right units, choose my machine, set my stock, and then I run what we call the auto feature recognition. And at this point, what CAMWorks is doing, it's looking at the faces of the model, and it's identifying 2.5 axis milling features and turning features. So what's a feature? A feature is essentially, what are we cutting? So some examples of features in milling would be countersunk holes or counterbore holes, bosses, slots, part perimeters. These are the actual physical features that we're cutting. In turning, we have ID features, OD features, groove features, facing and cutoff, essentially. So I analyzed the part. Notice over here on the left-hand side, it created 3 setups, a turn setup and 2 mill setups. A setup in CAMWorks terms is a direction that we are machining from. Okay, so it created 1 turn setup, and on that it created a face feature. And this may be difficult to see. I'm going to zoom in here. These are going to be highlighted in neon green. So here's the face feature. It's basically facing off to start off the cut. The OD feature, see if we can get kind of the side view here. It's just following the contour of the OD. Okay. Notice up here, it lifts off the part. The reason why that is happening is because it's actually looking at the full revolve shape. So to get this hump over here, it knows that it can only make the cut down that deep. It does the same for the ID feature, the inside here, and then the cutoff on this side. On the milling, you grab this group of countersunk holes, this group, and this group here. Right? These are actually threaded holes, and we'll deal with that in a minute. So this is the standard process. Is I'll run feature recognition, and I'll essentially filter out what it gives me. Okay, this is a realistic view as to what feature recognition does. It's going to give me some features that are perfect. It's going to give me some features that are unusable. It's going to give me features that are great, but I'm not going to use them that way, or I'm not going to cut them. So there's always some filtering. I'm going to be removing some features. I'm going to be rearranging features, and I'm also going to be adding my own features. But it's really a shortcut, right? It did a lot of this. It did a lot of the setup for me. So let's talk about some of the things that I'm going to need to change here. Maybe first we'll talk about what it gave me. So it gave me 1 turn setup, assuming I'm going to cut the whole part from one direction. Well, I mentioned I'm not going to do that, right? At some point in the program, I'm going to transfer it back to the subspindle, and I'm going to cut it from the opposite direction. So I'm actually going to need a second turn setup here. So I'm going to insert a new turn setup. I'm going to set the direction. Now these features I can actually reuse. Like the OD feature, doesn't matter what direction I'm going to be cutting from, it's the same feature. So I can control, click, and drag, and I can copy that feature from one setup to the next. And I'm going to do the same for the ID feature. So now I'm going to be able to cut that from 2 directions. This cutoff feature, I'm actually not going to need it because I'll probably just face that off once I transfer it, right? So I can do 2 things. I can suppress that, if you're familiar with SolidWorks, or I can just delete it and get rid of it altogether. I'm going to delete that. If you look closely here at the names of the features,
we have the feature type, and this, say, for example, this ID feature. It's called ID feature 1. That's the name of the feature. And then in brackets, we have the word drill. That word is what we call the strategy. The strategy is how you're going to approach a certain feature. Okay? So in this case, with the ID feature, it's a strategy called drill. The strategy that you have chosen kind of dictates what comes out of that database that I mentioned before. So I'm not going to touch this yet. We'll come back to this, but I want you to be aware of there's some other things going on here, namely that strategy. Okay, so going back to what it gave us 2 mill part setups, but it gave them in the opposite order that I'm going to cut them. So I might flip-flop them. I'll just grab them and drag one underneath the next. That takes care of the order. This whole group is correct. It also has the wrong strategy, but we'll talk about that in a bit. Let's talk about what it didn't give me. So we'll look at the features here. It did not give me anything to cut this shape here. So we can do that manually. Depending on how my machine is set up, I might have to cut this one way or another. So remember, we're cutting this on a lathe with live tooling. And the lathes with live tooling are, in most cases, are 2-axis. Sometimes they're 3-axis where they have a y-axis. And I would actually cut this feature differently if I had a y-axis or if I didn't. If I did have a y-axis, I'd want to cut it, say, from this direction and just go around this boss here. That's if I had a y-axis. If I don't have a y-axis, I'm actually going to have to cut it from the side, say spiral along here. So maybe we'll create it both ways so you guys can see the difference. With the y-axis, it's fairly simple. It's a 2.5-axis feature. So I'm going to go to my setup. I'm going to add a 2.5-axis feature. Remember, I mentioned 2.5-axis features are flat bottom features. So here's a list. We've got pockets, slots, bosses, holes, face features, and then we have some features that are meant to follow curves or sketches. In this case, it's going to be a boss feature. So to create this feature, I'm going to click on this top face, and it's going to automatically pick up the outer edges. And now it's going to want to know how deep is the feature. So I'm going to click on this face on the flange. So if you're a SolidWorks user, this will make a lot of sense to you. Instead of saying this boss is 0.59 inches deep, I'm using this up to face command. And now the feature is defined by the faces of the model. So this is one of the great things about running a CAM program within SolidWorks, is that you can take advantage of the parametric nature of SolidWorks. We know in SolidWorks, if we do an extrude up to face, or if we do a cut through all, if we change the shape of the model, those cuts or those extrudes update, right? Well, the same thing happens inside CAMWorks. With this boss feature, by saying up to face, if that flange ever moves, the definition of my feature changes and my toolpaths follow. So I don't have to redo my toolpaths. So here's where we choose this strategy that I mentioned. And the strategy is how you're going to cut this. So in this case, I've got fine, coarse, taper, slot. These dictate, when I run these through the database, these features through the database, these dictate what's going to come out of it. So for example, if I choose fine, it might just create a finish mill, or what we call a contour mill. If I choose coarse, it might just create a rough mill. Okay? So I'm going to choose fine in this case, and finish. So that's creating a 2.5-axis feature manually, and we created that because it didn't come out of the feature recognition. When you're using the software after a while, you'll start to be able to predict what's going to come out of feature recognition or not. I knew this wasn't going to come out because of this instance here. It's basically the shape of the feature is not exactly what CAMWorks thinks a boss feature should be. So that's basically why that happened. So I would cut this as a boss if I had a 3-axis machine. If I had a 2-axis machine, we'd cut it differently. And I'll create that. I'll come back and create that in a bit here. Before I go on and I make any more features, actually let's do one more. Let's cut this logo in, and then I'm going to generate some toolpaths. Because I really do want you guys to get the sense of how quickly this happens. Because I've been talking a lot here, but I actually haven't done much. So let's get some toolpaths on here and then come back and do some stuff. So I'm going to quickly create this feature. So this feature is just an engraving, essentially, of our logo, 5 thousandths deep. This is concentric to the rotational axis of the part. And because of that, it's kind of its special own CAMWorks feature. We call it a wrap feature. So in order to create this, I'm going to have to first create a new setup that's from the side. In that direction there, exactly. We'll pull this down to the bottom of the list, and I'm going to add a wrap feature. And wrap features are just 2.5 axis features that are wrapped around a cylinder. So this is going to be considered a pocket. I can click the faces just like I did with the boss. And then to tell it how deep, I'm going to click this outer face. And again, these are all up to face. So now this is all correct. The strategy that I'm choosing is rough and finish. So this is going to rough it and finish it out. So it created 3 separate pockets here. All right, so that was fairly simple, but that's a 4-axis cut. Let's run these through the database. So we call that generating operation plan. And at this point, when I click generate operation plan, what it's doing is it's taking these features and it's looking at certain parameters of these features. Things like the feature type, the feature shape, the feature depth, also the material that I'm cutting from, and the feature size. It's looking at all of those parameters and tabulating them. And then it's running each feature against our database. And it's looking for instances of where we cut something similar in the past. And when it finds that entry tells it how to handle that part. Okay, that's what's happening in the background here. So while I was talking there, it did all of that. It kicked me over to the next tab over here, the operation tab. And see, we have our setups again. And now we have what we call operations listed. And operations are actually the cuts. Okay, these are our rough turning, finish turning, center drills, drill, countersink, all of that. Okay, so what it came up with on, say, the turn setup, it roughed and finished the face. It roughed and finished the OD. On this mill part, on these countersunk holes, it created a center drill, a drill, and a countersink. Okay, it did all of that just by us telling it this is a countersunk hole. It chose all of those operations. It also chose all of the details as well. It chose the tool, chose the feeds and speeds. It also chose, say, the depths of cut, or in this case, pecking, or how we're going to drill it. All of our NC tabs, all of the nitty-gritty details of the toolpath. Okay, so last step here is I'm going to generate a toolpath, and it's essentially just going to take all of the details that are here inside each operation and apply it to the specific geometry of the part. All right, so if we look at the side here, I've got the rough face highlighted, and we look at the toolpath. What you see here, the red dotted line is rapid moves. The blue line is a feed move, where it's actually cutting material. Anytime I have a turning feature highlighted, you'll also see this orange, basically up. It's a real-time work in progress. So it's showing me the outline of the stock after this operation is cut, which is important because turning automatically always looks at the work in progress and only cuts where it needs to be cut. Looking at a mill toolpath, here's that boss. Right? So we can kind of see how that's working. It's using a 1/2-inch flat end mill. No lead-ins or lead-outs right now, and it's taken 3 depths of cut. So besides the features that I added and a little bit of rearranging here, I've only made a few clicks. Okay, so most of this came out right away. It's not perfect though, and that's basically how it's going to be, because it does rely on what you've done in the past. Not all parts are exactly the same. But what we'll find here is that most of what it gives me, I don't have to touch. It's going to be very little. So we're saving a lot of time over having to come up and create each one of these very manually, because within literally a handful of clicks, I have over a dozen different toolpaths here that very nearly cut the part. There's going to be a couple issues here. One of them, when I highlighted that center drill, I noticed it's a very large tool. Go to the tool, and on one side it would be fine, but on this side it looks like it will probably hit the boss that we created. So that's a relatively easy fix. We can go to our tool crib that we set up, and we could choose a different center drill. So I'll choose a smaller center drill here. I'm going to make a quick adjustment to the shank and preview that. So this, if you notice, this isn't a cigarette out here. That's actually a tool. It's following my cursor. It's not following any sort of tool path. What I'm trying to do is just get a quick visual look at what's happening. It looks like the tool is going to be small enough. Great. So I'm going to hit OK. I just changed my tool. Now what happens if I want to use that same tool on all of the other center drills? Because I don't need an extra tool, right? I can do that. I can link these operations. So if I link these two operations, they're now going to use all the same parameters. So if I change one, I change the other. What about down here in the pockets? So these are fairly small features. Here's the rough mill and the contour mill. Same sort of idea we can use. I could probably assume that all of these rough mills are going to be the same, and all of these contour mills are going to be the same. So I can click the rough mills and say combine, and now I just have one rough mill that controls all three. And I can do the same with the contour. Combine those. So that's going to make it easier when I have to come and edit this. If I need to, I only have to change one and it will change all of those together. So if anybody out there has Eagleeyes, they might have noticed that when I come back to the feature tree, a couple of these features stayed pink. And what pink means is the next step in the workflow hasn't happened yet. And so for this ID, and that would happen for a couple reasons. In this case, it didn't find a matching entry in the database. And that really has to do with the strategy that we chose, or the default strategy that came out of the feature recognition of drill. This is a chord stock. If we look at the stock here, it's chord. So it doesn't make sense to have to drill that out first, right? So I'm going to come in here and I'm going to change that strategy to something like coarse. I'm going to do it for both. And I'm going to generate operation plans for those now. So now I'm going to rerun them through the database, and notice it's going to kick me over to the operation tree, and now I have 4 new operations. I have rough boring and finish boring, and rough boring and finish boring. So I'll generate toolpaths on those. All right, let's take a quick look at the turning toolpaths. We'll start with the rough turn. So looking at it from the side, we can see the work in progress here is the yellow line, or the orange line, excuse me. Turning is great about dipping into nooks and crannies if it can. Now, we can stop that from doing it if we want to. In this case, I don't. But it's great at looking at the work in progress here. And it's actually showing me how close I'm actually cutting. So we notice this orange line is kind of off the part. It's not quite getting as deep as it needs. And even when I go to the turning, now I'm highlighting the turning finish path, the tool path. I'm still not quite there. So I can know that without even simulating the part. We've got some stuff going on here that I probably want to prevent as well. if I'm going to be turning this, if I'm going to be transferring this part, I probably don't want this dip in the ID. That could cause some issues. So probably what I'll do is I'll end up pulling this toolpath back. Before I do that, I'm going to go look at the second. So here's the first rough turning. Okay, it's basically going across the entire part. It's missing some spaces here, here, and here because the tool can't fit in there. If I go look at the next turn from the opposite direction, look where it's touching. It's only touching the spaces where the last one didn't. It's working from the work in progress, and it does that automatically. That's the great thing about turning. So while it's on my mind, I'm going to come back to this rough turning, and I'm going to tell it, hey, you know what? Stop before you get to the end because I don't need you to go that far. I'm going to be cutting from that other side anyway. So this is really simple to do. We call it a Z-limit. And essentially I can tell it stop at an edge or stop at a vertex. So I just click that edge, I hit preview, and very quickly it updates. Now it's stopping short. That's exactly what I needed. So I'm going to go ahead and accept that. I'm going to do the same for the turning, or the finish, I should say. Click that same edge, preview that, pulls it back, perfect. One thing I am going to try to do is I'm going to try to adjust the tool so on this finish pass I can get as deep as I need to. And I can do that just by choosing a different insert or adjusting the insert. So if I zoom out, I can kind of see what the insert's doing. It's a pretty large insert, and the lead angle could be straightened out a bit. So maybe I'll bump this down to, say, 15-degree included angle, and -1 lead angle. Now when I simulate, that tool's able to fit in. Perfect. Since I changed the tool, CAMWorks is now asking me what it wants me to do. Do I want it to create a new tool and add that to the tool crib? Or do I want to just change the existing tool? In this case, I think I'm going to add it. Because I changed the insert enough that that's a different insert. Now let's go take a look at our second turn rough and turn finish. Let's see if they've changed it all after we changed the first pass. Quite a bit, actually, over here. Turn finish looks good as well. So I think we're on to something there. We're going to have to do the same thing with the boring. So I'll come in and I'll limit the Z in the boring, because we really don't want these to go too far deep. It just doesn't make sense. So there's for the rough. And for the finish. I really only need to do this from one side because of that work in progress. So regenerate the toolpaths. And notice, again, now we have the same sort of instance. It's stopping halfway through. Let's run a quick simulation here to see how close we are. So what you're looking at, this is a representation of the stock and the tools moving across the stock and removing material. It looks like we probably need to rearrange the order of some of these on that opposite side. All right, so now it's doing the engraving on that little logo that we created really quickly, and it's done. So if I want to know how accurately I'm cutting this, or if I'm gouging it all, or if I'm missing any features, I can run a comparison. And what the comparison does is it color codes the part and shows me where I'm undercut or overcut. So wherever it's green, it's considered right on, If you see yellow or red, I'm overcut, and if you see some blue, I'm undercut. I think I might be slightly undercut down in this groove here. No, I'm only undercut because of the radius on the turning insert and the fact that there's a sharp corner in the model. So that's a case where I just have to say, you know, I probably can't do that, and if they need it done, then we're going to have to figure out a different way to cut this. It looks like I am undercut on the hole, not quite deep enough on the hole, and that's an easy fix. So if we find that the drill operation on that hole, there's a setting to include the tip length. So that will stretch it a little bit deeper, and we'll be deep enough on that. I was slightly gouging over here, so that's a matter of tool choice. I'm maybe running a little bit low on time, so I don't know if I'm going to address that, but that's a good way of knowing that, you know what, the shank of my tool is too large, so I need to narrow that down a bit. Let's see, I promised that I'd show how to cut this outer boss feature with a 2-axis lathe, so we'll do that. That's going to be done from the side, so it's going to be this setup here in the X direction. This is what we call a multi-surface feature. So multi-surface features come up when we're doing 3-axis cuts or 4-axis or 5-axis simultaneous cuts. We essentially tell CAMWorks what faces to cut. So I'm going to choose these faces along the outside here real quick. And CAMWorks is only going to want to cut these faces. So the tools that we're going to have available to us, because this is considered a 4-axis cut, will be pretty complex. I could probably spend a few hours just talking about that particular type of cut. So now I have all of my my faces selected. I'll select a strategy. In this case, it's going to be 5-axis. Select OK. I'll generate an operation plan for this. And we'll take a look at what it gave me. So it shows a 1/4-inch ball nose end mill. Looks like it's good size, going to be long enough. I'm going to have to do a couple of different things. Instead of 5-axis, I'm going to limit this down to 4. I'm going to tell it to point at the rotary. I have to tell it how to pass over these features. So we have lots of options. We can slice over the part. We can go across the part. We can choose curves to flow between. That's what I'm going to do. We can choose surfaces to flow between. Lots of power here. You can cut all sorts of geometry. You can do undercuts. We're going to do flow between curves. Now it's going to want me to choose the curves. I pre-made these, so I've got my upper curve and my lower curve. I'm essentially choosing the top and bottom edges of this feature. Hopefully you can see that. When I preview this, it's going to interpolate the toolpath between the two edges. This could take a second here to generate. I think I have CAMWorks XConnect running in the background. CAMWorks XConnect, if you haven't heard of it, it's a way to kind of offload the generation of your toolpaths onto an Amazon.com cloud server. And it frees up your computer resources, but the first time it runs, it always takes a second to start up here and ask me whether or not I want to offload those or not. So we'll go ahead and say local execution. So if you've seen that pop up, that's what it is. If I was running some intense 5-axis toolpaths that could take a long time, and I need to use that computer, I can offload them to Amazon web servers, and it chugs the numbers for me. It's actually pretty neat technology. So there we go. It's fairly simple to create that 4-axis cut. It's just going to interpolate between each side. Again, I can go into a lot of details on that, but in the interest of time, I just wanted to show you a pretty simple way to do this. And I would only need to do this if I'm cutting on a 2-axis machine, which I am. So I actually have most of this part simulated, or toolpath. I need to do a little bit more work on rearranging these. I need to get this mill set up above this one. I also need to put in the transfer. I think that's the last step in this puzzle here. So one of the newest things about CAMWorks is this ability to insert SubSpindle operations. SubSpindle operations are great for advanced lathes that have subspindle control. So a second spindle or an active tailstock that can come grab the part, it can transfer the part, it can measure the part, whatever it does, right? We can set up templates to do all of the codes for you. So I'm going to create a new main spindle setup here. I'm going to drag it after that mill part setup. In this, I'm going to insert a new subspindle operation. And right now, these are the available templates I have. Grabbing and pulling by a distance, grabbing and pulling, just grabbing the part. Standard transfer and just subspindle home. So in this case, I'm going to do a standard transfer. When I select this, it's going to bring me some options to control the spindle speed. So if I needed the spindles to be moving when I transferred for some reason, I could set that up. Orienting the spindle. These are all the steps that are going to be posted out to your code. And it's easy as that. It's basically a template to input your values in. So when I come to post-process this, let's post this out. So now it's actually writing the code. I'll speed this up a bit. And I apologize. I think we're going to run over a little bit over an hour, so hopefully everybody has time to stay with us here. I'm almost to the machine simulator. Okay, so now I need to open up the file that it created. Go to I'm using a dual turret post, so it created a post for the front turret and the rear turret. It opened up the front, which was empty, so I need to open up the rear, which is where all my programming is. So here is actually opened up right to where I wanted it. The transfer start, we've got it labeled right here. This is the transfer code that I just put in right into the program. So it does the transfer, gives you an optional stop, and then goes on and starts cutting the backside. Pretty neat, right? And very simple to do inside CAMWorks. So this part's essentially done. I mean, we programmed it in about a half an hour, and that was me talking through it. The use of auto feature recognition helped out a lot on this part. The use of the database to pull in my best practices, what I know works for past parts, helped out a lot because I didn't have to go through and pick all my tools. Or the feeds and speeds, or the depths of cut, or the NC planes, or anything like that. Okay, so now the G-code simulation. I'll probably get a hard time for doing this, but I'm not going to simulate this part here. Like I said, the G-code simulator is so new that I barely had any time to use it. I've had a license for just a couple days now, and I'm still learning it myself. So I set up a different part that's a little bit simpler than this to run on the simulator beforehand. So I'm gonna hop over to that part. This is just one of the example mill turn parts that comes with CAMWorks. I am going to quickly run feature recognition on this. This is a mill turn part, just to see what it gives us. 1, 2, 3 clicks. And I've got quite a bit of toolpath on there. Roughing, finish. No facing because there's no stock there. Let's simulate this. I'm actually not quite sure how good it's going to come out. Not too bad, actually. if we run a comparison on this, the only thing it missed is that back side. That's 3 clicks. I like that. That's awesome. Okay, so I did this beforehand. I set it up. I programmed this full part. I've got a few different turn setups, some milling setups. I have a transfer, okay, and then turning the back side. So I set this all up actually earlier this morning. And now I'm gonna simulate this on the G-code simulator. So the G-code simulator is accessed through the machine simulation. I'm given a standard option or a G-code option. They both open up the same piece of software, but one uses APT code, APTCL code, so kind of generic, it's not quite G-code, and then the other one reads G-code. So the second option is what I'm going to use. And when we choose this G-code option, it's very important that we have our machine simulator set up with the correct machine, and that our post processor is selected as well. I did all of that beforehand. All right, so now this is opening up the CAMWorks machine simulator. This is a kind of a separate program that's accessed through CAMWorks. This comes in 3 different levels: a standard, which runs the APTCL code; professional, which is what I'm running right now, which runs G code; and then a premium edition that can actually run standalone. I can open it up and I can read in G code from that was created in other CAM programs if I have that, if I work with multiple CAM programs. So this is a first. Integrated true G-code machine simulator. So I opened up the G-code that I just created over here on the left-hand side. I've got my machine set up over here. So take a look. It automatically read in my tools and the tool positions. I have a subspindle and main spindle. Here's my stock. In this case, the stock was a sketch, so we're fairly close to the shape already. It also brought in the chucks from CAMWorks. So I can run this a few different ways. I can run it line by line. So as I click line by line, notice it's reading down on the left-hand side in the G-code. And once I get past this little intro here, we'll start to get into some machine movements. All right, so now we've got some machine movements going on. Really what we're checking for are collisions between the turret and the stock, or the holders and the stock, or the chucks, all of that. These are very complex machines that have complex G-code, and it's just nearly impossible to read it just by your eyes and know what's going to happen, right? If I want to see the toolpath traces, I can turn those on. So now I got some traces in here. I can also do kind of a split view. Do 2 views. One showing the machine and one kind of showing the workpiece. So what's going to happen here when I play this, now it's playing, if there are any collisions, it's going to stop and it's going to warn me. So it's removing the stock the same way we see inside CAMWorks, but now it's also checking for collisions throughout the entire machine environment. We have the full machine kinematics here. We can do mill turn machines up to 8 axis, so dual spindles, dual turrets. We can do gang tooling, live tooling. When it comes to milling, we can do 5-axis milling. That could be head, table, head, table, anything that's out there. I'm going to pause that and turn the traces off real quick. And watch closely here. We're getting close to the transfer.
So over here on the right hand side, you'll see the transfer happen. And then it will start to machine the back side. So here it is, it's coming up, grabbing the part. And now it's still reading the G code, and now it's machining the back side as well. Kind of move that into view. So that's kind of the machine code, or the machine tools simulator in a nutshell. I'm just noticing that there's a problem with the chat window. I don't think it's available to you guys. So I'm going to pull up my email address here, and I'll just answer questions as they come to me through email. I'm more than welcome you to email me any questions you have, or if you want to see anything that I showed you in a little bit more depth, I'm happy to answer those. And I apologize for that chat window. I kept looking up at it and noticing that nobody was typing anything, and I was getting kind of sad, but now it looks like it's not working. So if I vet this out through the G-code simulator, then I can take this code to my machine with confidence, right? That's the whole thing here, is that, you know, there's one thing to program something perfectly inside your CAM software, but it's a whole other thing to have it run perfectly on the machine. And that's what we're trying to do with the CAMWorks Machine Tool Simulator. This is a sneak peek. I wish I could show you guys more. I'm not that versed in it yet. I'll be there. So maybe CAMWorks 201, which is in a couple weeks here, I'll show a little bit more Machine Tool Simulator. The 201 webinar is going to be more geared towards tips and tricks. People who have been using the software for a while now and want to know more about how they can optimize their technology database, how they can avoid some of the common pitfalls that we see in our tech support cases, some kind of some suggestions on how to squeeze the most out of the software. So that's really going to be the focus of it, where this was more simplified. So I thank you guys for watching this webinar today. I hope to see you guys all again on the 201 show, which is December 3rd, I believe. If you got the invite for this one, you'd get the invite for that one. Let me pull up my email address here. So if you missed it, I'm Tyler Reed. I'm the CAMWorks product specialist here at GoEngineer. I'm in charge of all technical aspects of CAMWorks at GoEngineer. Please, please, please email me any questions you have, support cases that you have, or anything else you think I might be able to help you with. If you want this slide set, I'll give you that. And if you want these parts, I can give you those as well. All right, so thank you guys for joining me, and hope to hear from you.